So up to this point, we've talked about using continuous variables to predict an outcome variable, but sometimes it's also helpful to have categorical or dummy variables used as our independent variables to predict our outcome variable. So going back to our Butler Trucking Company, the previous independent variables we've considered, such as miles traveled and number of deliveries, have been quantitative. But the new variable of rush hour is a categorical variable. It's also called a dummy variable. Will this dummy variable add valuable information to our current Butler Trucking regression model? So let's do a review of the residuals produced by the current model to help us make an initial assessment. We can create a frequency distribution and a histogram of the residuals for driving assignment that include travel on a congested segment of a highway during an afternoon rush hour period. And when we create a frequency distribution and a histogram of the residuals for driving assignments that did not include travel on a congested segment of the highway during the afternoon rush period. And so we can see those two histograms here. Now, we know that the residual for the ith observation is E sub I equals Y sub I minus Y hat sub I, which is the difference between the observed and the predicted values of that dependent variable. And the histograms here show that driving assignments that included travel on congested segment of a highway during an afternoon rush hour period tended to have positive residuals, which means we're generally under-predicting the travel time for those driving assignments. Conversely, driving assignments that did not include travel on a congested segment of a highway during an afternoon rush hour period tended to have negative residuals, which means that they were generally over-predicting the travel times for those driving assignments. These results suggest that the dummy variable could potentially explain a substantial portion of the variance in travel time that is unexplained by the current model. And so we're going to proceed by adding our dummy variable x sub 3 to our current Butler Trucking multiple regression model. Here's an example of what the multiple linear regression output would look like should you do it in Excel. Basically, the thing that we need to take away from this is that our estimated regression equation is y hat equals negative 0.3302 plus 0.0672 times x sub 1 plus 0.6735 x sub 2 plus 0.9980 times x sub 3. So how do we interpret this? Okay, so basically our model is going to estimate that travel time increases by 0.0672 hours for every increase in 1 mile traveled, holding constant the number of deliveries and whether the driving assignment route requires the driver to travel on the congested segment of a highway during the afternoon rush hour period. And then we have the other value of 0.6735, and that's going to be hours of every delivery, holding constant the number of miles traveled and whether the driving assignment route requires the driver to travel on the congested segment of a highway during the afternoon rush hour period. So when we look at our categorical independent variables, the model is going to estimate that travel time increased by almost an hour if driving assignment routes required the driver to travel on a congested segment of the highway during rush hour period, holding everything else constant. And we had an R-squared value of 0.8838, which indicated that the regression model now explains approximately 88.4% of the variability in the travel time for driving assignments in our sample. So here we have our two different equations. We're looking at the mean expected value time when there's no rush hour, so when x sub 3 is 0, versus when x sub 3 equals 1. And so when we compare these equations, we see that the mean travel time is a linear function of x1 and x2 for both driving assignments that include travel on the congested segment of highway during the afternoon rush hour period and driving assignments that do not. Beta 1 and beta 2 are the same in both equations, but the y-intercept value is going to differ. And so the y-intercept is that b naught, which is the first value in the equation, and b naught plus b3 in the second. The interpretation of beta 3 is that it is the difference between the mean travel time for driving assignments that include travel on the congested segment of highway during afternoon rush hour period and the mean travel time for driving assignments that do not. For our Butler Trucking Company example, if beta 3 is positive, the mean travel time for driving assignments that include travel on congested segments of highway during afternoon rush hour period exceeds the mean travel time for driving assignments that do not. If beta 3 is negative, the mean travel time for driving assignments that include travel on the congested segment of highway during afternoon rush hour period is less than the travel time for driving assignments that do not. And finally, if beta 3 is 0, then that means that there's no difference in the mean travel time for the driving assignments that include travel on congested segment of highway during the afternoon rush hour period and the mean travel time for driving assignments that do not. So if we take our independent variables and we put them in there, we see our same equations where it essentially ends up giving us the same values. So if we have more complex categorical variables, let's say our categorical variable has k levels. So maybe I'm looking at 3 regions, A, B, and C. K minus 1 dummy variables are required. And the reason for this is you want to have one of your dummy variables not included in the model itself so that you're not double dipping. So when we look at this, they're going to be coded as ones or zeros. So if initially in your data set A was 1, B was 2, C was 3, you're going to make those 3 separate dummy variables, and one of them is going to be left out from when you make your model. And so going back to our sales region example, we have our categorical variables with 3 levels. So we get to have 2 dummy variables. And so they're going to be coded as x1 and x2. And so when we make our model, it's going to end up looking like this. And remember that beta naught is your mean or expected value of sales for region A. Beta 1 is the difference between the mean number of units sold in region B and the mean number of units sold in region A. And beta 2 is the difference between the mean number of units sold in region C and the mean number of units sold in region A.